GRB 221009A is the brightest gamma ray burst of all time. We have detected since the 1970s, well, we being space satellites, gamma ray satellites, about 10,000 gamma ray bursts. And this is by far the brightest by not just a little bit, but by 100 times. It's a hugely different event, and based on the brightness and its proximity to us, we expect it to be a once-in-a-century event, which means this is the only chance in our lifetime to study this type of explosion at such a nearby distance in exquisite detail and actually be able to follow it across the electromagnetic spectrum for a very long time to come. One of the things that first captured my attention about GRBs is just how explosive they are, how bright. The amount of energy that they release in the span of just a few seconds is actually more than our sun produces over its entire lifetime. And the reasons that we like to study GRBs and the things we can learn about them have to do with star formation. So these long-duration gamma ray bursts are caused by the collapse of massive stars, and we can observe them due to their brightness all the way back to the first stars. So as we begin to probe these really high redshift, very distant gamma ray bursts, we can learn about how stars first formed, what environments they're forming in, what type of elements were existing at these times, and see how this star formation actually evolved over the history of the universe. This explosion that we observed is going to be detectable for at least a year, is the current estimate, and it could even go on for longer. So right now we're just trying to obtain the best data set we can at optical, infrared, radio, and X-ray wavelengths. And once we put together this data set, we can begin to model the explosion properties, and that will be when we really get to shed some light on how different this explosion was and whether there's some new physical processes that are going on that we need to start considering when studying gamma ray bursts.